Hello, my friends, and welcome back to the You Can Do TV channel. Recycling old and damaged vehicles begins with the collection process, during which end-of-life cars are transported to a scrapyard. Upon arrival, the dismantling process starts with the help of a crane equipped with hydraulic claws. These hydraulic claws lift and move the vehicles efficiently, allowing for the removal of large components such as doors, hoods, and trunks. This makes subsequent handling and processing easier and more efficient. Once the major parts are removed, the stripped car bodies are fed into an automobile shredder. This machine compresses the car bodies into compact blocks or cubes. Compressing the vehicle bodies significantly reduces their volume, making them easier to store and transport. This shredding and compacting process not only saves space, but also enhances efficiency throughout the recycling chain. By reducing bulk and separating useful materials, this method allows for the recovery of metals and other recyclable components in an organized and cost-effective manner. The overall process contributes significantly to resource conservation and environmental protection by minimizing waste and promoting the reuse of valuable materials. In summary, recycling vehicles is a multi-step process involving collection, dismantling with hydraulic equipment, and compacting with shredders to maximize storage, transportation, and material recovery efficiency. Steel making. The hot metal is transported to the Völklingen plant, where it is processed in 3 LD converters, BOF, each with a capacity of 180 tons. Here, the iron is converted into liquid steel through oxygen blowing. Secondary metallurgy processes, such as twin ladle furnaces, RH vacuum degassing, and alloying stations, are then used to refine the steel. Continuous casting. The refined liquid steel is cast into billets or blooms using 4 continuous casting machines. Saarstahl was one of the first companies to implement MSR technology, which significantly improves the internal quality of the steel by reducing central segregation. Burbach Rolling Mill produces wire rods with diameters ranging from 4.5 to 18 millimeters. Rolling. The cast products are then processed in various rolling mills to produce the final steel products. Völklingen Rolling Mill specializes in high-precision bar steel. Saarstahl is one of Germany's leading steel manufacturers. The company's steel production includes the following main stages. Half 1. Hot metal production. At the Dillingen plant, hot metal is produced in blast furnaces, operated by Rogesa Roheisengesellschaft Saar. The necessary coke is supplied by ZKS, a central coking plant. Neunkirchen Rolling Mill combines bar and wire rod production using thermomechanical rolling technology to enhance mechanical properties. Low carbon dioxide steel production. Saarstahl is also advancing sustainable steelmaking through electric arc furnace (EAF) technology at its Ascoval plant in France, significantly reducing carbon dioxide emissions by up to 70% compared to traditional blast furnace methods. 15. The forging die production process at MSV Metal Studénka involves a series of interconnected steps that ensure strength, precision, and durability in the final components. To begin with, the process starts with the careful selection of raw materials. High-quality steel blocks are chosen due to their excellent mechanical properties, particularly resistance to deformation and wear. Next, the steel blocks are moved to a heating furnace, where they are heated to a specific forging temperature. This heating process is essential, as it increases the metal's plasticity and allows it to be shaped without cracking. The temperature is precisely controlled to ensure consistency and prevent overheating. Following the heating stage, the hot steel pieces are transferred to the forging press. At this point, the actual forging process takes place, using powerful hydraulic presses and closed dies. The softened steel is formed into the desired shape under extremely high pressure. This stage significantly improves the material's internal grain structure, thereby enhancing its strength and reliability. Once the forging is complete, the excess material, also known as flash, that is pushed out of the die during pressing must be removed. Therefore, the next step is trimming. The forged parts are placed into trimming presses, which precisely cut off the unwanted edges and give the product a cleaner outline. After trimming, the parts undergo a crucial step: heat treatment. This includes quenching and tempering, which further optimize the mechanical properties of the forged components, such as hardness, strength, and toughness. Heat treatment also relieves internal stresses developed during the forging process. Subsequently, the heat-treated parts are cleaned using shot blasting techniques. This surface cleaning method removes any scale or oxide layers, leaving the surface clean and ready for further machining. Then, the components are taken to CNC machining centers for precision finishing. Here, all critical surfaces are machined to tight tolerances, ensuring that the final product meets exact dimensional specifications. Complex contours, threads, and holes are also created during this stage. Following machining, each part undergoes strict quality control. Various tests and inspections are carried out, including dimensional checks, hardness tests, and non-destructive evaluation methods. These measures are implemented to ensure the components conform to the company's high standards. Finally, after all quality requirements are satisfied, the components are assembled if needed, carefully cleaned, and then packed securely for shipment to customers. The production of leaf springs for trailers and trucks involves a series of carefully controlled steps to ensure durability and performance. The process begins with material stock preparation, where high-quality spring steel is selected and inspected for any defects. Next, the steel is cut into appropriate lengths based on the specifications of each leaf spring design. After cutting, the steel strips often have some deformation, so they undergo spring straightening to ensure uniform shape and alignment. Once the material is approved, it is stored in designated areas for easy access during production. Once straightened, the material moves to the hole punching stage. Precise holes are punched to accommodate bolts, clamps, or other connection components. Following that, the ends of each leaf are shaped through tapering, where the thickness gradually reduces to improve flexibility and distribute stress evenly. Then, in the eye forming process, the ends of the main leaf are curled into circular eyes using a press. These eyes are later used to attach the leaf spring to the vehicle's frame. After forming, the steel undergoes quenching, where it is heated to high temperatures and then rapidly cooled in oil to harden the material. Subsequently, the leaf is tempered in a controlled heating process to reduce brittleness and improve toughness. Following tempering, the springs are subjected to shot peening, where small steel balls are blasted onto the surface to introduce compressive stress, increasing fatigue resistance. Afterwards, the leaves go through rivet pressing, where center bolts and clamps are securely fastened. Small clippers may be attached to maintain alignment of the stacked leaves. Then, each leaf is coated in a protective paint layer to resist corrosion. Next, the individual leaves are assembled into a complete spring pack and pre-pressed to ensure they fit together properly. The entire unit is then painted again for a finished appearance and added protection. Before packaging, all assemblies undergo strict quality control (QC) checks, including dimension testing, hardness inspection, and surface finish evaluation. Once approved, the leaf springs are packed, labeled, and sent to the warehouse for storage or shipment to customers. In summary, each step in the process is crucial to producing high-quality, reliable leaf springs that meet the demands of heavy-duty transportation. At Forgiatura Morandini, the steel forging process begins with preforming, where steel ingots are heated to optimal temperatures and roughly shaped to prepare for the main forging stage. During main forging, the preformed billets are processed using advanced hydraulic presses ranging from 1,000 to 16,000 tons. These presses are controlled by PLC systems, ensuring high precision. Large furnaces maintain uniform and localized temperatures throughout the process. After forging, the components undergo hot rolling, where Morandini's state-of-the-art rolling machines shape the final product. These machines can produce seamless rings and special shapes up to 8,000 millimeters in diameter, 4,000 millimeters in height, and 150,000 kilograms in weight. Finally, the products are subjected to heat treatment to enhance mechanical properties and machining for final dimensions and finishing. The steel forming process at the company uses a 4-column hydraulic press installed below floor level to ensure high stability during heavy-duty operations. This powerful system is capable of shaping large and heavy steel components. The press features a free-fall control system combined with sliding rails, delivering precise and forceful impacts of up to 50 tons, ideal for forging and forming large shafts. Advanced automation and an electronic control system support the operation of the press and metal handling equipment, enhancing both efficiency and safety throughout the process. At Simex, the forging process begins with selecting high-quality steel bars, which are heated to optimal forging temperatures. These heated bars are then shaped using precision forging equipment to form the initial structure of the crusher bucket shafts. Following forging, the components undergo controlled cooling to relieve internal stresses. Once cooled, the shafts are subjected to cold working processes, utilizing numerical control machines to achieve precise dimensions and tolerances. This step enhances the mechanical properties of the components, ensuring increased hardness and durability. Subsequently, the shafts receive specialized anti-wear treatments, significantly boosting their resistance to abrasion and extending their operational lifespan. The final stage involves meticulous quality control checks, where each component is inspected to verify conformity to strict standards. This comprehensive forging process ensures that Simex crusher buckets deliver exceptional performance, reliability, and longevity in demanding operational conditions. The hammer forging process for ring rolling begins with the preparation of a cylindrical metal billet, which is first heated to a forging temperature to ensure it becomes sufficiently malleable. Once heated, the billet is transferred to an anvil where it undergoes upsetting. During this stage, repeated vertical hammer blows are applied to compress the billet in height and expand its diameter, improving its grain flow and strength. Next, the billet is pierced at its center using a punch, creating a hole that transforms it into a donut-shaped preform suitable for ring rolling. Following this, the preform is reheated to maintain its plasticity before being positioned onto the mandrel or idler roll of the ring rolling machine. Subsequently, the idler roll presses the preform against the drive roll, which rotates and gradually reduces the wall thickness while expanding the inner and outer diameters of the ring. At the same time, axial rolls may be employed to control the vertical height of the ring and ensure dimensional accuracy. As the process continues, the ring expands uniformly until it reaches the required dimensions. Finally, the finished ring is removed from the machine, resulting in a seamless, high-strength component with refined mechanical properties. This integrated forging and rolling technique produces rings that are widely used in demanding applications across various industries due to their durability and structural integrity. The forging process using a 250 kilogram hammer begins by heating the iron or steel workpiece in a furnace until it reaches a bright yellow or orange color, indicating it has become sufficiently malleable for shaping. Once heated, the operator quickly removes the piece using long-handled tongs and immediately positions it on the flat anvil surface beneath the hammer, ensuring the workpiece is aligned correctly for effective forming. Next, the operator initiates the hammering process by pressing the foot control, causing the hammer to deliver strong, rhythmic blows onto the hot metal. With each strike, the material is compressed and gradually transformed from its original shape into a rough version of the desired form. Then, without delay, the blacksmith rotates or repositions the workpiece between hammer strokes to achieve uniform deformation on all necessary sides, allowing for balanced shaping and symmetry. After the initial forming, the operator continues forging with increased precision, carefully adjusting the angle and intensity of the blows to define specific features such as tapers, curves, or edges. This stage requires skill and speed as the metal begins to lose heat during the shaping process, becoming less ductile. Finally, once the desired shape is reached, and while the material is still hot, the blacksmith uses a flat tool or die under the hammer to smooth out the surfaces and achieve finer detail. In this process, a rotating multi-point cutting tool, known as a milling cutter, is used to remove material from a workpiece by advancing it in a direction at an angle with the axis of the tool. The setup begins with securing the metal workpiece on a rigid machine bed or table using clamps or vices. The milling machine, typically a CNC vertical or horizontal type, positions the cutter precisely relative to the workpiece. Once the machine is set up, the cutting tool is powered to rotate at high speeds. The table moves the workpiece against the rotating tool along multiple axes, X, Y, and Z, allowing for complex shapes and surfaces to be machined. Face milling removes material from the surface of the workpiece, creating a flat and smooth finish. Side milling cuts along the side of the workpiece, while slotting creates keyways or grooves. The machine feeds are carefully controlled to ensure consistency and accuracy. Coolant is often applied during the milling process to reduce heat buildup and prolong tool life. Precision measurement tools are used to verify dimensions throughout the process. Overall, power milling offers versatility, accuracy, and efficiency in producing parts used in automotive, aerospace, and general engineering industries. It is suitable for high-volume production and allows for automated programmable operations using CNC technology. Gear machining process using invomilling. The first machining step involves roughing the internal gear teeth using a 10 mm solid carbide end mill, VHM end mill. The tool engages the workpiece through helical interpolation, gradually removing excess material along the intended tooth path. The tool path is programmed to approximate the involute profile and clear the majority of the stock material efficiently. This operation focuses on high material removal rates while maintaining enough precision to allow for finishing in subsequent steps. Proper cooling and chip evacuation are applied to avoid tool wear and maintain dimensional stability. Once the roughing is complete, the gear flanks are finished machined using an invomilling cutter provided by Sandvik Coromant. This specialized tool is designed to accurately generate the involute tooth profile using synchronized multi-axis toolpaths. Unlike conventional gear cutting, invomilling allows the use of a standard milling machine to produce different gear sizes and profiles by simply adjusting the CNC program. The cutter moves along a circular path while maintaining a constant orientation to simulate the motion of a traditional hob. This finishing operation achieves the required profile accuracy, surface finish, and dimensional tolerance of the gear teeth. Machine parameters are optimized to minimize vibration and ensure a smooth cut. In the final step, the tooth root, bottomland, is finished using an 8 mm ball nose end mill. The tool is guided through the root area to remove remaining material and create a smooth transition between the gear flanks. This process eliminates sharp corners and reduces stress concentrations, which is crucial for extending the gear's fatigue life. The ball end geometry ensures a uniform surface finish at the root radius and enhances the gear's overall performance. The manufacturing process of automotive lead-acid batteries involves a series of precise steps to ensure quality and performance. It begins with the strip mill, where lead sheets are rolled to the desired thickness. These sheets are then used in plate making, forming the positive and negative plates essential for battery function. In the assembly line, these plates are inserted into battery cases, separated by insulating materials to prevent short circuits. The cases are then sealed, using heat seal techniques to ensure airtightness. Terminal burning follows, where terminals are securely attached to the battery, providing connection points for the vehicle's electrical system. A state of charge indicator is installed to allow users to monitor the battery's charge level. Subsequently, the electrolyte, a mixture of sulfuric acid and water, is filled into the battery cells. The formation process then activates the battery by charging it, forming the necessary chemical structures within the plates. Finishing touches include the application of a double lid for added protection and a final pressure test to ensure there are no leaks. The battery is then cleaned to remove any contaminants. Load testing is conducted to verify the battery's performance under simulated conditions. Finally, labeling is applied, providing essential information such as specifications and safety warnings. The steel bars are then loaded onto carriers and inserted into a microwave furnace for heating. Upon exiting, optical sensors detect and record the temperature, which is displayed as a digital chart to monitor quality and consistency. After heating, the bars are cut into billets according to required dimensions. These billets are then preformed using a hydraulic press to give them a rough shape, close to the final product. The core forming stage is performed with forging hammers, magli, that apply forces from 16,000 to 31,000 kgm, depending on the product. Each part may weigh between 15 and 200 kg. The hammers are mounted on a vibration damping system that reduces ground vibration by up to 90%. Different types of steel bars are received, sorted, and assigned a barcode for tracking. A digitized system ensures full traceability of each bar from warehouse entry to the final production stage. ISAC is a specialized Italian company producing custom-designed steel components using a modern and highly automated production system. This step is performed in a dedicated department equipped with automated and digitally controlled machinery. Finally, forged parts are trimmed using edge presses and transported via conveyor belts for further processing or inspection. The Özkoç Makina hydraulic press operates through a precise and automated process. Initially, a metal sheet is positioned onto the die within the press. The hydraulic system then activates, exerting controlled pressure to form the metal into the desired shape. After forming, the press retracts, and the shaped component is removed. This sequence ensures consistent production of high-quality metal parts with minimal manual intervention. The procedure begins with securely mounting a flat metal disc onto the machine's rotating spindle. Once the disc is in place, the CNC program initiates the spinning operation. As the spindle rotates the metal disc at high speed, a forming tool, controlled by the CNC system, presses against the disc. This tool gradually shapes the metal over a predefined mandrel, transforming the flat disc into a symmetrical, hollow component. Throughout the process, the machine adjusts the tool's position and pressure to ensure uniform thickness and precise dimensions. The CNC system allows for consistent replication of complex shapes with minimal manual intervention. This automation enhances production efficiency and ensures high-quality results. Upon completion, the finished part is removed, and the machine is ready to process the next piece, maintaining a continuous workflow. The metal forming process on the Denzen 100 CNC spinning machine begins with clamping the metal blank onto the main spindle. Once the machine starts, the spindle rotates at high speed while the forming roller gradually presses against the blank, performing the spinning operation to shape the material according to a predefined mold. Next, the machine carries out shear forming to trim excess material and achieve the desired dimensions. Following that, the beading process is performed, creating grooves or ridges on the part to enhance rigidity and aesthetics. Finally, the finished product is inspected and removed from the machine. The entire operation is fully automated, ensuring high precision and efficiency. The aluminum casting process involves several critical steps to ensure high-quality, defect-free components. It begins with professional staff training, where workers are trained in safety protocols, equipment handling, and process control. Next is the designing of foundry tools, where casting molds and related tools are designed using CAD software and then machined for precision and durability. The process continues with melting of alloy in an electric or gas furnace at approximately 660 degrees Celsius. Once melted, the molten alloy degassing step is carried out using inert gases like argon or flux agents to remove dissolved hydrogen and oxides, minimizing porosity in the final casting. Before casting, a milling cutter is used to prepare test samples, which are then analyzed using a spectrometer for chemical analysis to verify the alloy composition. Modification and refinement of the molten alloy is performed by adding elements such as strontium or titanium to refine grain structure and improve mechanical properties. In the low-pressure casting stage, the molten aluminum is pushed into the mold cavity using low gas pressure, ensuring uniform flow and reducing turbulence. This step is followed by casting into the molds, where the metal solidifies to form the desired component. After solidification, parts undergo stationary X-ray inspection to detect internal defects such as porosity, cracks, or inclusions. A product traceability system assigns a unique identifier to each casting for quality tracking. To clean the parts, dry ice blasting is used to remove surface residues without damaging the component. The castings then go through quality control processes, including dimensional checks and visual inspection. Mechanical testing includes HB hardness testing to assess material strength and helium leak detection to ensure air tightness, especially for pressure-critical parts. Finally, the castings undergo output check and dispatch, where they are packaged and shipped after final verification, ensuring only high-quality products reach the customer. The construction of a 20,000-gallon stainless steel tank begins with rolling large steel plates into curved sections. These are then welded together to form the tank's cylindrical body. Next, the bottom and top heads are fabricated separately and welded in place. Internal components, such as baffles and reinforcing rings, are also installed. After welding, all seams are carefully inspected and polished to ensure strength and hygiene. The tank is then fitted with nozzles, manways, and support structures. A lifting system is used to move and position the tank for final assembly. Once completed, the tank undergoes pressure testing to verify its integrity. Finally, the exterior is polished for a clean finish. This process ensures the tank meets sanitary and structural standards required for industrial use, particularly in food, beverage, or pharmaceutical applications. The hot forming process for dished ends begins with heating flat metal sheets, typically made of stainless steel, carbon steel. These sheets are placed into a furnace and heated to a temperature between 800 degrees Celsius and 1,200 degrees Celsius, depending on the material type and thickness. The goal of this step is to soften the metal, making it more malleable for forming. Once the sheet reaches the required temperature, it is quickly transferred to the forming station. There, a hydraulic or mechanical press is used to apply high pressure, shaping the heated sheet into the desired dished form. Precision dies are employed to control the curvature and depth accurately, ensuring the final shape meets strict dimensional tolerances. The elevated temperature reduces the material's resistance to deformation, allowing for smoother forming with less residual stress. This stage is critical for achieving high-quality dish ends, suitable for pressure vessels and similar applications. First, the turbine blade workpiece is securely clamped onto a multi-axis CNC machine. Accurate fixturing is crucial to ensure stable cutting conditions and high precision during the machining process. Next, the roughing stage begins. At this point, a Kennametal ceramic end mill is used at extremely high cutting speeds, reaching up to several thousand meters per minute. Due to the ceramic tool's excellent heat resistance, no coolant is required. The tool rapidly removes the majority of excess material, shaping the blade to a near-net form. Ceramic tools maintain performance under intense heat and stress, making them ideal for machining hard materials like inconel. The turbine blade machining process using Kennametal's standard ceramic tools involves two main stages: roughing and finishing. This modern method is particularly effective when working with heat-resistant superalloys such as inconel. Then, the process moves to the finishing stage. The same ceramic tool is used, but this time with a reduced feed rate and shallower depth of cut. The goal here is to achieve precise geometry and a high-quality surface finish. The ceramic cutter maintains sharpness and dimensional accuracy over long cycles, which minimizes the need for tool changes and post-processing. The result is a smooth, accurate blade surface that meets strict aerospace or power generation standards.